We want to basically generalize the idea of area under the curve using Riemann sum. So that is what is called as definite integral. So in definite integral, you do the following. So you have a continuous function on a closed interval AB, like here. So you have a continuous function. Let's call this function as f of x. And you have a continuous function on a closed interval AB. Then you divide AB into n equal parts, each of with delta x. So delta x is going to be b minus a by n, right? Then what you do is, then you have these set of points. So the first point is x0. The next point is going to be x0 plus delta x, or rather a plus delta x. This point is going to be a plus 2 delta x, and so on and so forth. So this is what you do. X0 is a, x1 is this, blah, 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 to b. These are the endpoints of the interval, where xi is a plus I delta x. This gives the endpoint. Now recall we took the left hand point for the height once and the right hand point for the height once. In this case, we'll choose any point. So you saw that the left hand point did not matter really, it gave us the same area. The right hand point also gave us the same area. So we'll choose xi star to be any point in interval x0, x1. Any point, it doesn't matter. So what you do is you take any point here. This will be your x1 star. Any point, as long as the function is continuous, it doesn't matter. It will give you the same answer when you take the limit, and then you construct this rectangle. So what do you get? You get f of xi star delta x. So for x1, you will have x1 here, right? Plus f of x2 star delta x, where x2 is any point between, where x2 star is any point. It doesn't matter what point in x1, x2. So on and so forth. So you keep on doing this all the way until f of xn star delta x. And if I write this in the summation notation, I'll get summation I going from 1 to n, f of xi star, this is x1 by the way, delta x. And then when you take the limit as n goes to infinity of this, you get the actual area, right? This thing will be defined as integral a to b fx dx. Yeah, note that this is a special example where f of x is greater than 0, but here we are not asking for, so it is not necessary that f of x has to be greater than 0. It can also be less than 0. We'll see in a minute what does it mean, what does it represents. So this is the definition of the definite integral of f of x from a to b with respect to x. So let's just write down the terminologies. So this is a definite integral a to b fx dx. Here, this curly s sign, this is what is called as integral sign. The f of x is a function you are integrating, so you call it as integrand. A and b are called limits of integration. A is the lower limit because it's below here, and b is the upper limit. And the procedure of computing an integral is called integration. And this sum is called Riemann sum. This is named after a famous German mathematician, Bernhard Riemann, who actually has similar ideas and came up with the concept of Riemann integrals. So that's the idea behind the integral. So now few facts we need to understand about this guy. So fact one, If f of x is greater than 0, then some on AB, then integral a to b fx dx is greater than 0. Now this basically represents, because it represents the area, right? That's why if basically integral a to b fx dx is greater than 0, then this is greater than 0. Similarly, if f of x is less than 0, say suppose this is your f of x and this is the area, then if f of x is less than 0, then it represents the area, this area, but with a negative sign. All right. There's another way to look at this. Another way to look at this is the following. This is given by limit as n goes to infinity of summation what n I going from 1 to n f of xi star delta x. Now, if your function, so delta x is positive, if f of xi star is positive for each I, which is the case because f of x is greater than 0, that means you're multiplying two positive quantities. So that will be positive. You're adding positive quantities, so that's going to be positive, and you're taking limit as n goes to infinity, it will be definitely greater than 0. So on with the other one as well. Okay. In general, it represents what? It represents the, if you're looking at integral a to b fx dx, so let's look at an example. So suppose this is my function like that. Suppose this area is A1, area being the positive quantity. This area is A1. This area is suppose A2. And suppose this area is A3. Then the integral basically A to B fx dx represents the sine area of the region or the net area, which is area above the x-axis. So area above the x-axis is A1 plus A3 minus area below the x-axis. So below the x-axis would be minus A2. So this is what the integral represents. Okay. So B. Now C says the following, that what C is telling you is that integral A to B fx dx and this Riemann sum are epsilon close to each other. You can always find a Riemann sum which is epsilon close to the actual integral. Okay, so it's saying that you can approximate with some n. If you take the Riemann sum, you can approximate that integral within the epsilon error. Now, the next one is saying the following. Let f be a continuous function, and you take partition to be delta xi as xi minus 1, and suppose maximum of delta xi approaches 0 as n tends to infinity, then integral a to b f of x dx is going to be this limit. Here in this case, they are saying that the sample, so in this case, you don't have delta x, but you have what? Delta xi. So the width of the rectangle is also variable. So it's saying as long as the width of rectangle is getting really very small, it doesn't matter what width you take. So the width can be variable as well. Okay. Now, few more facts you need to know while solving a problem. So summation I going from 1 to n I is n into n plus 1 divided by 2. Summation I square, I going from 1 to n is n into n plus 1 times 2n plus 1 divided by 6. Summation I going from 1 to n of I cube is same as the formula for summation I, as you notice, except this is squared. Summation I going from 1 to n of C is you're adding Cn times, so it's Cn. If you have CAI, you can take out the C. So you get C summation I going to 1 to n from AI. And next one is AI plus or minus BI. If you're taking the summation, then you can break the summation as I going from 1 to n, summation AI plus or minus summation BI. So these are the few. Okay. Now you can prove this using mathematical induction, or we can basically prove it in the next class about it. Okay. Now note that this rule is not true for multiplication, by the way. bi is not equal to summation I going from 1 to n of ai, summation I going from 1 to n of bi. So this is not true for multiplication, neither it's true for division. So you have to be careful about those things. So not true for addition and basically multiplication. So this is not true for them. So let's try to do the following problem. So could you try to do 0 to 2 x squared minus x dx? So let's try to do this together. So in this case, what is my delta x? Delta x is going to be 2 minus 0 by n, which is 2 by n. Now, what is my integral? 0 to 2 of x squared minus x dx is going to be summation I going from 1 to n f of xi star delta x, and then you're taking limit as n goes to infinity. Now xi star is any point between xi minus 1 and xi. So first of all, what are these xi? Xi is going to be 0 plus I delta x, which is going to be 0 plus I delta x. So we can take, that is going to be 2 times 2 divided by n multiplied by I. So instead of multiplying in the front, I'm multiplying in the back. Now note that it is any point, xi star is any point in what? Xi star is any point in 2 by ni and 2 by ni. So we will choose any point in between, but when you want to choose a random point, why not choose a point which looks nice? So we'll choose this guy as a point. So this can be, this is going to be summation n equal going to infinity, summation I going from 1 to n, f of 2 by n I. Yeah, we want to choose a point which can be properly what represented. So 2 by n. So now this is going to be, let's write it down, limit as n goes to infinity. I can take summation. So this is going to be summation I going from 1 to n. We have 2i by n. What is f of 2i by n? F of x equals to x squared minus x. So f of 2i by n is going to be 2i by n the whole square minus 2i by n multiplied by 2 by n. So let's multiply this out. So this is going to be limit as n goes to infinity, summation I going from 1 to n. 2 square is going to be 4, 4 by n square multiplied by this 2 by n as well. So it's going to be 8 by n cube times I square. And the next one is going to be 4 by n square times I. Now we can break the summation. So summation of, as we saw, summation of ai minus bi is summation ai minus summation bi. So we'll break that. We'll have 8 by n cube common. I have summation I going from 1 to n of I square. For the next part, I have summation I going from 1 to n of 4 by n square. Now we can use the formulas for summation I square. We already know that. What is that? N going to infinity, 8 by n cube. What is formula for summation I square? N into n plus 1 into 2n plus 1 divided by 6 minus 4 by n square times summation I formula is n into n plus 1 divided by 2. Now we'll try to take this limit. First we'll simplify it a bit. N going to infinity, 8 by 6. Now I have n cube here. I'll distribute it each to 1n. So n by n, which is 1. 1 plus 1 by n and then the third n will go in, and we have 2 plus 1 by n. Similarly, here we'll have 4 times 1 divided by 2. This 2 will come here, 1 plus 1 by n. And limit as n goes to infinity of this is going to be 8 by 6, which is same as 4 by 3 times 2 minus 4 by 2, which is going to be 4 by 2 is 2. So this is going to be 8 by 3 minus 2, which is going to be 8 by 3 minus 6 by 3, which is going to be 2 by 3. So this is your definite integral. So now we are given this sum. Can we write this as an integral? Okay. So what integral does this Riemann sum represent? So you can see that this represents integral pi to 2 pi 1 plus x cos x dx. Okay. Now, prove that 0 to 2, 4 minus x squared dx is pi. So, well, for now, one can basically write this as limit as n goes to infinity, summation I going from 1 to n, square root of 4 minus, what is delta x in this case? Delta x is 2 minus 0 by n, which is 2 by n. So 2 by n I square times 2 by n. Of course, computing like this is going to be difficult for us. Why? Because we don't even have summation formulas for square root. Later on, when we make formulas for or techniques for integration, you'll see how to do it properly. For now, we will basically use the graphing to see what it is about. Okay, so let's look at this function. So you have y square root of y minus x square is y. Now, what kind of function does this represent? So if you square on both sides, you'll see that 4 minus x square equals to y square. So this implies x square plus y square equals to 4. So this represents a circle. So this represents essentially a circle. So let's look at the circle. And this represents a circle of radius what? This represents a circle of radius 2. Now, the upper part of the circle, when you try to write it as a function of two variables, function of one variable, this is not a graph of a function, right? So when you try to write it as a function, there is an upper part, which is given by y equals to square root of 4 minus x squared. And then there's a lower part, which is given by y equals to minus 4 minus x squared. Okay. So what do we get? So this is a circle of radius 2. And now we are looking from 0 to 2. So first of all, this y 4 minus x square represents the whole upper semicircle, but you're only going from 0 to 2. So you're essentially looking at this area. Yeah. And you know what is the area of this? So area is going to be pi r square, which is 2 square, but we are only looking at the 1/4 of that part because circle is symmetric. So this is going to be pi, yeah, which is your integral 0 to 2. We'll later on learn on certain techniques on how to integrate, and then you'll use trigonometric substitution to do this. Yeah. Okay. So here the takeaway message is that the definition of area as an integral helps us out on how to find out this value. Now, Now, sometimes we are happy with an approximation. It may not be a precise approximation, but a good enough approximation. So one of that approximation is the midpoint rule. So what is, so integral a to b fx dx can be roughly written as summation I going from 1 to n f of xi bar delta x. What is xi bar? Xi bar is a midpoint of xi minus 1 xi. So midpoint is going to be xi minus 1 plus xi divided by 2. Now note that there's no limit being taken here. So this is an approximation, all right? So generally people are happy with the approximation, right? So for example, in a lot of your calculation, you use pi equals to 3.14 as an approximation, but pi is an irrational number. Yeah, the digits go on forever and the pattern does not repeat. Yeah, so same thing about integral as well. Sometimes approximation, you take a good enough approximation, you're happy with that. So let's do the following problem. So use midpoint rule with n equals to 4 to approximate the integral 1 to 5 dx x squared. So first of all, what we'll do is the following. So we will divide this into 4 intervals because n is what? 4. So you have 1 here and you have 5 here. Now, what is the length of each interval? It's going to be b minus a by n. So that is going to be 1. So the interval is going to be 1 to 2, 2 to 3, 3 to 4, and then 4 to 5. Now, so delta x is just 1. So delta x, so this integral 1 to 5, 1 by x squared dx. So delta x is basically 1. However, for the height, you're using what value? You're using the midpoint value. So what is the midpoint of 1 and 2? Is going to be 1.5. What is the midpoint of these two guys? Is 2.5. So these are the values you're using for the height. 3.5 and then here 4.5. So this integral is going to be equal to summation I going from 1 to 4 f of xi. Recall you had xi star, but here we are choosing a special point, which is the midpoint of the interval, delta x. You're not taking any limit, so this is an approximation. Yeah, it's a big approximation, all right? So this is going to be f of, what is the midpoint of the first interval? F of 1.5 times delta x, which is 1. F of 2.5 times delta x, which is 1. F of 3.5 delta x, which is 1. F of 4.5 times delta x, which is 1. So this is going to be equal to 1 upon, what is the function? Function f of x is 1 by x squared. So this is going to be 1 by 5 square plus 1 upon 2.5 square plus 1 upon 3.5 square and plus 1 upon 4.5 square. And when you'll approximate, this is approximately 0.735. Okay, you can add this up and check. The answer is going to be 0.71. Sorry, 735. So let's try to understand the properties of integral. So if you have integral a to b fx dx, that is same as minus a to b fx dx, right? So this is the one property of the integral. Yeah, so that makes sense, right? So, I mean, one reason for that is in this case, the delta x is, in the first case, the delta x is b minus a by n. In the second case, the delta x is what? In this case, the delta x is a minus b by n, right? That's one way of looking at it. Yeah. So if you flip the integral, then you change the sign. Similarly, if a equals to b, then integral a to b fx dx is 0, because you are essentially having a and b are same thing. You're finding area under a point, which is going to be 0. Now, few more things follow from the definition of the limit definition of the integral. Namely, if c is a constant, a to b c dx is c times b minus a. Yeah, well, you can think about it in the following way. So let me take c positive just as a special case. So my function is constant c. So then the area is going to be the base, the width is b minus a, and the height is what? The height is c. Similarly, if you follow the definition, you can see that integral a to b fx plus or minus g of x dx is going to be, you can break the integral. So it goes from a to b fx dx plus or minus a to b gx dx. Note that this is not true for multiplication or division. Okay, not true for those. Similarly, if you have a constant of integral, you can take the constant out. Now, another thing is, if you have integral, say a to b, and you take this integral, then integral a to b, so suppose c is any point, then integral a to b is this whole thing, right? So integral a to b of f of x dx is same as integral, you basically take a break in between, a to c f of x dx plus integral c to b f of x dx. Yeah, so essentially you're taking a break in between, right? You first compute this guy, and then you add it with this guy. Yeah, not only that, it is also true if we don't have, this is also true if c is not between, if what, if if we don't have, a less than c less than b. So c need not be between a and b, and still it is going to be true. Okay. Now let's look at the following example. So you have 0 to 3, 2 minus 3 times square root of 9 minus x squared dx. So again, so we can break this using the integral laws above. This is going to be 0 to 3, 2x dx minus 0 to 3, 3 times 9 minus x squared dx. Now this can be seen as 0 to 3 of x dx minus 3, 0 to 3 of 9 minus x squared dx. Now this again looks like what? This looks like what? 1/4 of a circle, right? Of radius, what? Radius 3. So this is going to be 1/4 of what? 3 square, right? This part is going to be 1/4 of 3 square, so minus. And now what about this guy? 0 to 3 of x dx. So either you compute it by using the Riemann sum, or you can also look at it from the area perspective. This is going to be, again, area of this rectangle. This is going to be 3, 3. So area of this triangle, sorry, area of this triangle is going to be, base is 3, height is 3. So we get 2 times what? Half base into height. Okay. So therefore, this is equal to 9 minus 9/4, which is, nobody corrected me, it's pi 3 square. So this is the answer. Okay. So we have this 3 as well. So I should put that 3. So 3 times this guy, which is going to be 9 minus 27 by 4 pi. Yeah. This is the integral. Later on, we'll see techniques on how to evaluate it directly without even appealing to the fact that it is area of a circle. So that will come soon. Now, can you do this problem, please? So you can break it into two parts now. So 0 to 1 fx dx plus 1 to 3 fx dx, right? So using the property of integral, so this is going to be 0 to 1 minus x dx plus, or rather, well, 1 to 3 minus of 1 minus x minus 2 the whole square dx. So now we can approach this again by looking at the area. So this one is, so the first part is 1 minus x. If you look at the graph, it looks like that. At 0, the value is 1. At 1, the value is 0. So it is this area. You could have done this directly using Riemann sum as well, or the limit of Riemann sum. This is 1, this is 1. Now let's try to understand this guy. So you have y equals to 1 minus x minus 2 square. So again, this looks like a circle really to me, a part of circle at least, right? So square on both sides, you get y square equals to 1 minus x minus 2 square, or x minus 2 square plus y square equals to 1. So let's see how does this guy looks like. So this is a circle of radius 1, but the center is what? Center is 2. So what is the center of this guy? Center is 2 comma 0, right? So if you look at this circle, the center of this circle is 2 comma 0. This point is 3. This point is 1. So this is how the circle looks like. And since you have the minus sign, you're looking at the bottom part of the curve. And you're looking from 1 to 3. So you're looking at this area. So this area is going to be, so this is going to be what? Area of the bottom area of the circle of radius 1. So this is going to be minus pi by 1 square divided by 2. Whereas the first one is going to be the area of this rectangle, which is half times 1 times 1. So the answer is half minus pi by 2. And if you want to simplify that, that turns out to be minus 0.7. So this is how you evaluate this integral. Okay. So now let's investigate few more properties of integral. So if f of x is greater than or equal to 0, then what we have, and your x is between a and b, then integral a to b fx dx is greater than 0. Because essentially you're looking at area under the curve. Same way, if f of x is greater than or equal to g of x, so the blue graph is bigger than g of x, then of course, if both of them are positive, you are essentially saying the area below f of x is bigger than the area below g of x, which is what the integral represents. This is true even otherwise. Next one is if your f is between small m and capital M, then what do you get? You will get the following. In this case, you have m is less than or equal to f of x. So think about this as a constant function. So you have integral a to b dx of this guy is going to be less than integral a to b dx. Now, this is basically what? if you look at this guy, this is simply a rectangle. So you have M here, A to B. So the area of this rectangle is going to be M times B minus A. So we have M times B minus A is greater than equal to integral A to B fx dx. And similarly, following on the other side, you can see that this is going to be less than equal to M times B minus A. Okay. Now let's use that to prove the following. 1 by e to the 4 is less than equal to this integral, which is less than 1 by e. So make a connection with C, and let's try to do this. So let's look at f of x equals to e to the power minus x squared. Now you're integrating this from 1 to 2. Now notice that this function is, this looks like the function is decreasing. Yep. Let's check that. How do you check whether function is decreasing? Using derivative. If you look at the derivative, you get minus, so e to the power minus x squared derivative is e to the power minus x squared multiplied by derivative of x squared, which is minus 2x. And this is less than 0 on 1 to what? 1 to 2. So that means the function is decreasing. Therefore, f is decreasing. Now, if you take a decreasing function, the highest value, the largest value of the function is at the initial point of the interval. So this means what? This means your f of 1 is what? Sorry, f of 1 is the largest value, and the smallest value happens to be at f of 2. So f of 2 is going to be less than equal to f of x, and that is going to be less than equal to f of 1 for all x in 1, 2. Right? Because it's a decreasing function, so the smallest value is at the end here, and the largest value is at the starting point, which is 1. Now, this is same as, but what is f of 2? F of 2 is going to be e to the power minus 4, or you can write it as 1 by e to the 4 is less than equal to what? F of x is less than equal to f of 1, which is e to the power minus 1. Now, if you integrate throughout, therefore integration of 1 to 2 of 1 by e to the 4 dx is less than equal to integral of 1 to 2 of f of x dx, which is less than equal to integral 1 to 2 of e to the minus 1 dx. Now, this is like a rectangle, right? I mean, this is following this property here. This one here, right? So now you get, this is going to be 1 by e to the 4 less than equal to integral 1 to 2 f of x, which is e to the minus x squared dx, less than equal to e to the power minus 1. And this is what you wanted to prove, right? Well, e to the minus 1 is same as 1 by e. So this take care of that proof. Now let's look at the following. So another property, if f is a continuous function on a, b, then integral a to b fx dx is less than equal to integral a to b fx dx. So now how do we basically go about it? Now note the following. So if you take any x, for any x, it follows from the definition of the modulus sign minus modulus of f of x and f of x. So this is the connection between this guy, right? So your f of x is always between minus modulus of f of x, this guy. Now, if you integrate on all sides, you will see that integral a to b fx dx is less than equal to integral a to b fx dx is going to be less than equal to integral a to b absolute value of fx dx. All right. So these are just numbers, right? Essentially. So what do we get? In this case, again, let's read it back in the let's read it back without the integral, without the absolute value sign. So you know the following. So if absolute value of x is less than equal to y, this is same as saying y is less than equal to x less than equal to y. This is a connection between the absolute value. So this is, so now we are going from this direction to this direction. So you can see that this would imply that absolute value of x dx is going to be less than equal to integral a to b. Okay. So now what is the upshot of this? Why is this result of any interest to us, or why is it useful to us? Now notice the following. So if I apply that result to this problem here, what would I get? I will get integral 0 to, so b, if I apply the same result to b, I'll get 0 to 2 pi absolute value of f of x sine 2x dx is going to be less than equal to 0 to 2 pi absolute value of f of x sine 2x dx. Now note that you know that sine, so let's simplify this a bit. So f of x sine 2x, if you look at the absolute value of this is the same as absolute value of f of x times absolute value of sine 2x. But what about sine 2x? So sine values are always between -1 and 1. So absolute value of sine 2x is always less than or equal to 1. So this is going to be less than equal to f of x. So again, if I apply this function is less than equal to this function, so integral of this is going to be less than equal to integral of this function. So you have proved that this is the result. Okay, so you are able to basically integrate it without getting the sign. Okay, so now if you want to look at graphically, you are saying essentially, so let's take f of x. So let's look at the following function, following result graphically. So here you have a function. So this is your f of x. And when you're integrating from a to b, you're finding the signed area. So if this is a1, this is a2, this is a3, then the integral represents a1 plus a3 minus a2. This is what your integral represents, a to b fx dx. And you're looking at absolute value of this thing when you're looking at absolute value of this guy. However, if you take absolute value of your function, then of course this function remains same. But here, since you're looking at the absolute value, you are getting this addition, and then you have this thing. So of course, clearly the integral of absolute value is bigger.